We ended really quickly looking at this. Do you guys want me to go back through the answers on this? Please do it. So, come on, pen. There we go. So in our startup, what we'll hopefully be starting to do is group and memorize reagents. When you see that boron with the peroxide, you should immediately be thinking you're adding H and OH. Okay? The question then is when and how do they get added? Okay? Step one in this case is the addition of the H. And so we're going to add our H to the pi bond, and we'll add our boron to the other half of the pi bond. Okay? Not a big deal in this one, but this is a syn addition. They get added on the same side. Why do they get added on the same side? Hydrogen is a horrible leaving group, which means it has to, the pi breaking off to attack the boron and the hydride coming back must happen simultaneously. So they're added on the same side. Okay? We don't like boron on our structure, so we'll eject that boron in the following step with our peroxide. Okay. Same general kind of idea. This is horribly drawn as a mechanism. I'll show you the mechanism here on the next slide. Okay. But your electrons come up, kick out, and we would end with the final result, H and OH. Notice the OH is being added in the exact same stereochemistry. Okay? This all has to do with that boron. We're reacting simultaneously onto that boron bond. Right? Why do we not need to specify the wedges and dashes on that blue structure? It's not a chiral molecule. That does become important when we move through to the next reactions, because when we move through or down to our next reactions, we're going to run the same reaction, and this next one is going to give us a little bit more information. In this case, we have to recognize where we place the H in the boron. In the first reaction, it didn't matter because both those carbons were identical. In the bottom case, it does matter because each of those positions is different. Right? If we remember that our boron is what's acting as the electrophile, that doesn't show up very obviously. Let's try that again. As our positive, the partial negative carbon is going to come out and react, which means the end result is that we're going to put our hydrogen at the more sterically hindered site. That makes that methyl dash. Everybody see that? Okay. Those are now both chiral atoms. We must specify wedges and dashes here, okay, or at least we should specify the wedges and dashes. It depends on the question asked, because it is possible that your answer choices aren't specifying wedges and dashes, so you don't need to worry about it. Yes?
You can do that on the bottom too, right? Add those on the bottom.
This can also happen on the bottom because it's an addition. All addition reactions are going to run the potential of forming two products. Okay. We then follow it again with our peroxide horrible mechanism that Mike draws. There's our dash, there's our wedged hydrogen, there's our wedged OH. What is interesting about that addition? If we went through and did this with H plus and H2O, okay, back from chapter 11, the end result is we still add H and OH, but notice the OH adds to the more substituted position. Okay? So you're still doing the same basic chemistry except your positions exchange. This is a very common reason why the boron reagent needs to be memorized, because it is placing the OH in a non-standard fashion. Okay? That non-standard is why that reaction is sometimes referred to, and we had this discussion, as non-Markovnikov. Okay? I still think it's dumb because all of the chemistry is identical. Okay? We still have a partial negative attacking a partial positive. It's the boron. The hydrogen's being added as H minus, which goes to the positive carbon on our pi bond. What happens with the other structure? The pi bond, our partial negative reacts with the positive. What's the positive in this case? Hydrogen, what's the negative? The oxygen. That's why we're getting the placement there. When we move to the boron reagent, oh my God, the results have all changed and everything's crazy and new. No, it's the exact same chemistry. The atom location appears to have changed. Okay? But if you follow the chemistry, there's no magic behind the atom location. The chemistry is still doing the exact same thing. Okay? This is why I don't like the use of Markovnikov. You want to use it, that's fine. Just realize there's limitations. Okay? We go on to the right-hand side of all of our answers. Now I'm going to erase that guy. Get that one back. Same general idea. If you can remember, if you want to remember anti-Markovnikov, okay, there's your OH and you've added your new H. Okay, I don't need to specify the H because it's non-chiral and it's a hydrogen. I don't have to specify the hydrogen, period. Okay. I also don't have a chiral atom here, so I don't need any wedges and dashes, but I've got my final answer. We go through with the last one. This one becomes trickier because we have 2 pi bonds. The chemistry is still the same. The chemistry does not change, and this is one of the things that is insanely cool about OChem, is that our chemistry runs the same path. We place our OH, we place our hydrogen. Okay? We could go through and run this a second time with another pi bond, but before we start initiating that, we need to recognize that we have an alkene and we have an alcohol. Those 2 functional groups are overlapping. I'm just going to say that says alcohol, okay? Which means in that happy middle ground, we have what is known as an enol. And from what we remember of chapter 7, the enol tautomerizes to take us to the carbonyl. We end with the aldehyde. Okay? That chemistry, I'm not going to draw out again. If you have questions about that enol-ketol tautomerization, that's fine. Talk to me after class, and I'll draw through it step by step.
Is it still called the keto-enol thing, even when it makes an aldehyde?
Yes, it's still called the keto-enol tautomerization. Yep.
Okay.
And yeah, you might ask, well, why do we still call it a keto-enol? And origins.
The chemistry is the same. I was just wondering if
The aldehyde is actually more reactive than the ketone. And so the aldehyde is typically found in the dialcohol, or can be found in a larger percentage in the dialcohol state, which we'll talk about in second semester.
Oh, okay.
Which means the ketone more readily transitions, which is why we refer to it as the keto-enol, because we see it happen more commonly with the ketone. Okay, but the aldehyde still does the same thing, okay, and to roughly the same extent. Okay. Here's the big, old, long mechanism behind the boron structure. Okay, if we looked at the reagents, it's peroxide and hydroxide. If you looked at the mechanism I drew, did I show anything happening with hydroxide? No. Is hydroxide important? Yeah. It's actually integral to the mechanism. Okay, that's the big, long mechanism that goes on through here. Okay, if you're interested in it, you can take a look at it. If you're not interested in it, don't worry about it. Okay? Ultimately, the bottom line is your stereochemistry is retained through the addition of H and OH with the boron reagent. Okay? Which then gets us up into, I kept forgetting this chapter, chapter 19. This is our reduction and oxidation chapter. Okay? So, reduction, gain of electrons, oxidation, loss of electrons. For those of you that memorized oil rig, you can leave now. Just checking. Leo says Gur is the better one. It was a joke. You don't have to leave. Okay. How is that useful for classifying this reaction? What is the oxidation state for the carbon?
I don't know. We have to check.
Okay. You'd have to check. Fun thing about it is if you go through and use your knowledge from Gen Chem about determining oxidation states, you'll end up getting a weird fractional value for it. And that's because this carbon's oxidation state is different from that one. In an individual structure, particularly organic chemistry, you will get varying oxidation states. They are not all the same. The rules that you learned in Gen Chem were fantastic for structures that all had the exact same oxidation state. Not the case anymore. So we need a different way to go through and apply this. Okay? Our organic tweak behind this reduction is increasing hydrogen bonds. So the more bonds to hydrogen you have, you've reduced it. Okay, so if we go through and take a look, let's pick our carbon. Red carbon. What happened to it?
It gained the hydrogen.
We drew in all the bonds. We've added a hydrogen. Okay? So that carbon was reduced. We increased the bonds to hydrogen. If you go through and check all the other carbons, well, 3 of the 4 remaining carbons, because 1 nothing happened to, okay, you check the other 3, they will all have been reduced. We've run a reduction reaction. Okay? So in that direction, it's a reduction. What if I go this way?
Then it's oxidized.
Okay, it's oxidized. How do you know it was oxidized?
Because of decrease in hydrogen bonds.
So, okay, thankfully you gave me that answer and not the smart-ass one of, well, it's the opposite of reduction, okay? Which is a fair answer. If we know that was reduction, then clearly the others have got to be oxidation.
That was my smart
Okay.
answer.
The oxidation is going to be a decrease in hydrogen bonds. So if you reference your reaction types based off of increasing hydrogen or decreasing hydrogen, you can classify reduction and oxidation, and that works pretty well. Okay? There are cases that it doesn't work as well for, so you could go through and reference oxygen bonds. How many oxygen bonds do you see?
0.
So that's not a good qualifier. Okay? And the oxygen bond 1 really isn't oxygens. Okay, what we're talking about, and this is not an easy one to write in here, but in both these cases, what we're referencing is an increase or a decrease in more electronegative atom bonds. So if we take a look at our red circled carbon, okay, what electronegative atoms is it connected to?
Carbon.
Carbon's electronegative?
I mean, everything is electronegative.
Okay. More electronegative.
None.
Okay. In comparison to the red carbon at the end, you'd still say none. There's no difference in electronegativity.
That's not true.
If we take a look at the left side, we're connected to an sp3 carbon and an sp2. If we look at the right-hand product, what do we got? All sp3 connections. What's the difference between sp3 and sp2?
Decrease S characteristic.
A change in the S characteristic. An sp2 hybrid atom is more electronegative. When we go from our reactant to our product following our red arrow, we decreased bonds to more electronegative elements. It actually holds. Okay? That requires that you use hybridization to classify things. How many of you are super comfortable with hybridization? You got 2 weeks to improve. Okay? Or you memorize and hope hydrogen bonds help out. Okay? Kind of makes sense? Both of them become tricky because we've got to deal with hybridization, or the other case, we've got to deal with hydrogen. Why was hydrogen tricky? Hydrogens are almost always implied. Okay? So you have to be a little bit careful with your oxidation and reduction when you qualify through a reaction to figure out what's going on with it. Sometimes it may require you to dig out into hybridization theory or specify all of your hydrogens. Okay? Both of those pieces you're going to have to balance. Okay? This is not coming up with an exact oxidation state. Okay? To do that, I might, I do kind of have that in here. Cardi talked about that in chapter 1. I mean, way early on in the semester, he talks about identifying oxidation states. I'm not positive this formula is correct, and I always have to check it. If you really need to figure out oxidation states, you can talk to me after class. Okay? So don't rely on that formula. Okay, but it might be right. I honestly don't know. Okay, we'll figure it out later. Okay. Minimally, if we look at all of those carbon structures, what could you tell me about them? Nothing? Is that what silence means?
2 of them are the same.
What do you mean two of them are the same?
4 and 5 are the same.
Okay, 1, 2, 3. Whoop, ho! Try that again. Saying 4 and 5 are the same literally because they are the same structure. That's fantastic, Mike.
You're welcome.
Happy to help. They have different numbers of oxygens.
Oxidation.
Okay. If we can look at these patterns, we can try and predict something about their oxidation states. This one is going to be fully reduced. How do you know that one's fully reduced? It's only got hydrogens. To our far right, we have fully oxidized. What was the oxidation state of carbon that you were told to memorize in Gen Chem?
I can't remember.
-2 unless bonded to.
That's interesting. It was actually kind of a trick question. You shouldn't have been told to memorize. Why are you told to not memorize carbon?
Because it always depends on what it's touching.
Depends on what it's connected to. Okay, so the oxidation state for carbon is exceptionally variable. Okay, it ranges from fully reduced smalls -4 up to +4. Every state in between is a possible oxidation state for oxygen or carbon. Okay? So you shouldn't have been told to memorize it. You might have been told -4. Okay? The -2 I find a little bit weird. Don't stress about it right now, Leslie. If you stumble across it later, that's
I thought you
okay.
said oxygen, not carbon. That's why I said -2.
Oh, well, I might have because I just screwed that up also. Oh, I didn't? You shook your head.
No, you said
I did say carbon? Okay. Because I know I started to say oxygen later. Okay, but anyways, -4 to +4 for carbon. So we can hit that full spectrum. What we're going to be responsible for doing is trying to identify what kind of reaction happened. Why do we want to know that? That can help zero in on the reagents. If I look at a reaction and know it's a substitution, should I be adding a base? No, because when is a base useful? Fair enough, in an acid-base reaction. So if I'm doing a substitution, I probably don't want to do an acid-base, so a base is probably a bad idea. I hadn't thought of that one. Give me another one.
Elimination.
In an elimination reaction, I need to remove that hydrogen so I can make the pi bond. Okay? So if I know the type of reaction that's happening, I can sometimes needle down the potential reagents that need to be used. This is why I've asked you to memorize those reaction types. It's to help give you that classification so that you can zero in on reagents. Why is that going to become important? Well, most of this section is now talking about reduction and oxidation. So you would need to know the reagents that allow you to do those transitions. Okay? So, come on. Label them. Reduction, oxidation, or neither. We'll number these. Left column, 1, 2, 3. Right column, 4, 5, 6. 1. This is an oxidation. What happened? We've lost a hydrogen and we've replaced it with a chlorine. We've increased the bonds to an electronegative atom. We've also decreased the number of hydrogens. Okay, next one. Okay. Didn't I increase hydrogen?
No.
Okay. Where we need to focus, okay, and because this is common for students, is to jump all over that hydrogen. We need to focus on the chemistry that's happening to our starting material. Where's the chemistry in that starting material? On that carbon. So when I go across to the product, that's the carbon I need to look at. What happened to it? Well, I lost a chlorine and I replaced it with oxygen. Chlorine was more electronegative than carbon, wasn't it?
Yes.
Yeah, so I lost an electronegative atom. Shouldn't that be reduction?
Then you gained an electron.
But then I gained one. The net result is nothing. Neither happened. Why is this neither? What kind of reaction did you do? Substitution. When we talked about substitution reactions, did we talk about oxidation states? No, why not? Because it ain't reduction and oxidation. That's why. Next one. Okay. We're looking at a reduction here. We've lost an oxygen and we replaced it with a hydrogen. 4. Oxidation. This one, admittedly, I always have to check myself on. Yes, we lost hydrogens. Okay. Yes. Okay, next one. Oxidation. We've increased oxygen bonds. Last one. Oxidation. We've increased oxygen bonds. Kind of makes sense? Do you have the picture yet, Lee? Are you good? Are there questions about it? Okay. So again, trying to at least get a grasp on that type of reaction can help out. Okay, so try and zero in on that. Okay. Where this becomes important is now what we'll look at is all of these reactions that are either reduction and oxidation. Okay, so when we look at an alkene, what's happening in each of these cases? Okay, let's look to that would be my right. What happened? We start with a pi bond, and what have we added? Oxygen. So what have we done? Oxidation. We've increased bonds to a more electronegative atom. Okay? So in each of these cases, we're doing oxidation. Okay? If we go back here, if we take a look at those last two reactions, how many oxidations did I do in the red box? That was only one oxidation. What did I do in the blue box? Soon to be blue box. This was 2 oxidations. Okay? So a molecule could potentially undergo multiple oxidations. Okay? Or it could stop along the way. Okay? What's going to dictate that? The reagent used, which means what do you need to know? The reagent used and which one does which. Okay? Along those pathways. The mechanisms for the oxidation and reduction reactions tend to be a little bit more complicated. And so with time and where we are in the semester and all that kind of fun stuff, I would kind of push that you should just memorize. Okay? We'll attempt to come up with a patterning behind these so that you can get a rough idea behind it. When we talk about second semester, I go right back in with these exact same reactions in second semester because I'm fully aware of how rushed we pushed through this. Right? But we'll look at some of these pieces and try and come up with patterns within them. Okay? We're still following that same kind of cyclic idea that we ran in the previous section. We're talking about our tri and tetra cyclic structures. Here we're now moving up to that penta intermediate. The common thing that you'll find is that they all have at least a 3-atom connection. Okay? If we look at permanganate, MnO4, there's a metal center with 4 oxygens. Okay? Or we have osmium tetroxide. There's a metal center with 4 oxygens. Okay? Same deal is going to happen when we look at, or not same deal, but the same kind of concept is going to happen with ozone. In the case of ozone, O3, we get this connection. Okay? In both cases, well, that's okay. We're still getting this basic kind of piece that allows us to connect out. Okay? So when we're looking at our alkene, the electrons come out, attack the oxygen. The electrons in that pi bond will go to the metal center. Why would they go to the metal center? Why would that metal want electrons? Because of all of the oxygens around it are all withdrawing electron density away. So the alkene now provides the opportunity for that metal to get some electrons back. So the alkene shares electrons in. We shuttle the electrons to the metal. But now what happens to the metal? It's now electron rich, so we have to push some electrons out. The electrons it pushes out are a pi bond on the other side. the end result is that we end up with, we don't need to go that far down, a 5-membered ring. Okay? The same thing's happening with the ozone. Okay? We still have our pi electrons. Does that center oxygen want to be positive? No. Could it act as an electrophile? Could the center oxygen accept more electrons from outside the structure? No, because
It's full octet, it's actually overloaded.
okay, it already has its octet. If we tried to bring more electrons in to stabilize it, does it have a weak pi bond to break? Not really. Where can we attack? We can actually attack the neutral oxygen. When the electrons come up to that neutral oxygen, these electrons slide over to the positive. We've now stabilized that positive oxygen. Okay? Because we're talking about a pi bond with an alkene, what's now forming out over here? Lee, you nodded. What's forming out there? A partial positive of our carbocation. The electrons can swing down in. And again, what do we end up with? That 5-membered ring. Okay? In this case, when we go through and look at it, the leaving group is a pi bond. Okay? So I would argue the leaving group in this case is fitting into that category of insanely small. Okay? It's so small, it's a pair of electrons. Okay? So it's not really leaving the structure, it's stuck within the structure, but the structure itself is able to react back and immediately stabilize our intermediates. Okay? And that's how we end up with all these other systems. Okay? So the easiest one to look at is going to be, didn't mean to pick that color, those two. What do you notice is the difference between the products of those two? Nothing. They're identical. You get the exact same products. Why would we get the exact same products?
Because you're doing the exact same mechanism.
If we look at the chemistry behind it, it's the exact same chemistry. It's a metal oxide reacting with a pi bond. Everything's the same. Notice what happens with our stereochemistry.
It's conserved in both cases.
Okay, it is conserved. I get two OHs added on the same side. Why would I get two OHs added on the same side? How did these two oxygens attack the pi bond?
On the same side.
On the same side. Okay? So the steric consideration and those structural considerations help to dictate the relationship between those groups. Okay? That can become helpful. Okay? This also shows up in a similar type reaction known as the DielsAlder. There is a video for you to watch on DielsAlder. Okay? That is all of the content that I'm going to give you on DielsAlder is straight up out of that video. Okay? And I kind of hate to admit it, the only reason I'm doing that is because allegedly someone said that it's supposed to be talked about in first semester. I have not been in a single institution that thinks DielsAlder should be in first semester. Everybody thinks it belongs in second semester. The only institution that says it should be in first semester is Maricopa. Literally the only one. Everybody does it as the very first lab in second semester. Okay? So up to you how much you want to hold in that video. Okay? But that video has DielsAlder reaction in it. That is now my stamp saying you've now received it. Okay? And you have that content. It matches the patterns, okay, that we've talked about here with that metal oxide system. Okay? This one gets a little bit more complicated. Pi bond reacts, pi bond moves, pi bond reacts. Kind of like the exact same arrows that we've already been showing. Yeah, it's because it is. Okay? Pi bond reacts, pi bond shifts. It's the exact same process. Okay? Except we've now added an extra atom in it, which means in our final product, instead of being a 5-membered ring, we get a 6-membered ring. Okay? That's it. Okay? The DielsAlder becomes infinitely more complicated because
Electrons electron donating withdrawing groups.
We could talk about electron donating versus withdrawing behind these. This double bond could be cis or trans. What could this double bond be? Cis or trans. This double bond. Cis or trans. Is the stereochemistry now locked into place? It is. Which means depending on which of those positions you start with, the orientation of the individual groups hanging off are all going to be dictated from the get-go in the beginning. You have to be able to predict out wedges and dashes on a multitude of different positions. It turns into a giant nightmare of a reaction to deal with when we're thinking about stereochemistry. Okay? Second semester. Okay? Or you memorize the crap out of it. The video gives you the cheat on how to just memorize the rules for it. Okay? I literally just give it to you because I know it's that hard to spatially deal with. Okay? But it is a fascinating reaction. Nobel Prize, okay, for the DielsAlder. But yeah, we'll talk about more second semester. So, if we look at our osmium, just like our permanganate, okay, we already looked at the basics of the mechanism. The osmium oxide bonds to the pi bond, we get our 5-membered ring. Okay? If we want to get fancy, we can call this an osmate ester. What is an ester?
Something with, yeah.
Something with a yeah? There's an ester. Okay? We've got a carbonyl with an oxygen connected to it and another carbon. Okay? If we go through, do we have an ester?
Yes.
Where's the carbonyl in the ester?
It's, well, I guess this is part of
Define a carbonyl.
carboxylic acid.
Define a carbonyl.
Double bond.
A carbon-oxygen double bond. Do we have a carbon-oxygen double bond? Stop talking about that piece.
Oh,
No. Okay, we're talking about the osmium structure. Okay, so we don't have the carbonyl. Why are we referring to that piece as an osmate ester? Okay, the osmate is our tip-off that we're not talking about carbon. Okay, it's the osmium that's causing the ester. So if we look at the osmium, that osmium is our carbon with a double bond to an oxygen and a single bond to an oxygen that's then bonded onto a larger structure. That's why we call it an osmate ester. Okay, you could also hear of sulfur esters. Okay. All we're saying is that the center atom is different from carbon, okay? But it's still the same basic structure. Okay? The next thing you notice, how much of a mechanism are you responsible for going from the osmate ester to your final product?
several.
How many curved arrows do you see? None. Do you think you're responsible for that mechanism? No, you're not. That's why they're not shown. Ta-da! Okay? You don't need to worry about it. Okay? It's a complex mechanism that deals on a variety of different pieces, and it usually involves some more reagents. Okay? So if we look here, because we're going to do some slide jumping here in a second, we've got a final kind of reaction. You could be asked to predict the product. Okay? You should be able to predict this product, right? Really easily. You're like, oh, dude, that's way too hard. There's no way I could predict the product of a 1, 2, 3, 4 carbon butene with a carboxylic acid on the end of it. There's no way I could draw the answer that is already on the screen.
Predict the product? I want to say that it's
That's all you had to do. It was a massive typo. I shouldn't have asked the question. I should have asked a different structure. Okay? It's literally already on the screen. Okay? Do the oxygens have to be wedges?
No.
No, they could be.
Dashes.
Why could they both be dashes?
Because it's a pi bond.
Could have attacked from either side of the pi bond. Could we get one wedge, one dash?
No.
No. Again, that osmate ester, that 5-membered ring, that's why we talk about it. That's what's driving the chemistry. Okay, that stereochemistry at the end. Kind of makes sense? Okay, so here's some slide dancing. You see the reagents? OSO4, peroxide, butyric acid. No, terbutanol, sorry. 0 degrees Celsius, 16 hours, right? Okay, we gotta do some more slide dancing. What does that say?
Sodium.
Sodium, hydrogen sulfite, and water. Maybe NMO, question mark. 1, 2. What does 1, 2 mean?
2 steps.
2 steps. Does it say 2 steps?
No.
No. What the hell's going on here? Okay? Because guess what? Not only can we ask you to get to this product using that or the reagents I just had up on the other screen, you are also expected to show the final product given just OSO4. What do I mean? Do you need to know that secondary reagent? No. If you see OSO4, what do? Alcohols, we can do better than that. How many alcohols? 2 alcohols, known as?
Dialcohol or something?
Dialcohol is better. A diol. Okay? 2 alcohols. A diol. How are the alcohols added? Are they added on the same side, opposite sides, both sides? Same side. Okay, so this would be a syn addition of alcohols. So we end up with a syn diol. Syn dihydroxylation. What does dihydroxylation mean? Di, 2, hydroxy, 4, the oation, or the oations. Okay, for the alcohols, the ation is just the verb conjugation of it. Okay, kind of makes sense? So when you see OSO4, syn diol. Just do it. Okay, yes?
Does this happen with the manganate as well?
Does the manganate do the exact same thing? Yes. Yes, it does. You get the exact same result. Okay? Notice the yield gets a little bit worse. Okay? And I don't think we have the yield up on the other one, but the yield isn't all that great on this one. Okay? But there's an extra piece of information that we need to watch out for on this one. What might that extra piece of information be?
Cold.
Cold.
Dilute.
Those are actually the 2 big words that you need to remember. The hydroxide isn't a big deal. Okay? But it needs to be cold and it needs to be dilute. Okay? If those conditions are met, then you get the exact same result. Okay? Kind of makes sense? Yes?
Is that because the heat causes decomposition?
Okay. Blink for a second because I don't want to talk about the bottom one. Man, okay. We're just going to have to go the other direction. Cold and dilute, right? We get the diol. So let's go backwards a couple slides here. Cold and dilute potassium permanganate, we get the diol, where they're on the same side. What does that say? Potassium permanganate, hot, concentrated. So different conditions, but same reagent. We'd be like, oh, that does the same thing. Whoa. Something crazy, weird, and different happened there. Okay? Permanganate is an exceptionally strong oxidizing agent. What does that mean it does? It adds oxygens to a structure. It oxidizes things. So when we look at our reagent, we went from an alkene to oxygen bonds, the diol. Or we went from our alkene to a whole crap ton of oxygen bonds. Okay? So permanganate is such a strong oxidizing agent that if we don't put in harsh controls on it to slow it down, it just oxidizes the crap out of whatever it touches. How do we slow it down? You make it cold. How else can you slow it down? You don't put a lot of it in there. Okay? So if you control those conditions, you can minimize the oxidation. Okay? If you give it free rein, lots of heat and tons of reagent, all sorts of stuff happens. Okay? And that's how we shift into the last 3 reactions on this. What did all of those reactions do? Whoops, sorry, didn't mean to do that. What did all 3 of those reactions do? They oxidized. But didn't these also oxidize? So I don't quite accept your answer. Don't give me that face. Yeah, they oxidized. We have more oxygens. Okay. So they definitely both oxidized. So what's the difference between the red and the blue if they both oxidized? Okay. What happened to the red ones? You broke. What did you break? Okay. And so what I'm going to do is play off your words, because your words are good and it's something we need to watch out for. Okay. The suggestion was that we broke the cyclic structure. Did we break the cyclic structure? It's no longer a ring. It's not what I'm asking. What did we break? We entirely broke the pi bond. That's it. These reagents break that pi bond. It just so happens that that pi bond was in a cyclic structure. It does not have to be cyclic. What the reagents are doing is taking a pair of scissors and cutting the pi bond. And only that pi bond. Okay? So that's why I want you to be careful in the statement, well, we broke the cyclic. You broke a pi bond. The structure just happened to be cyclic. Does that make sense? Okay? So be careful with that phrasing. We got to be a little bit tentative there. Okay? So now we got to do a bunch of sliding around. Okay? What we're talking about here is what's known as oxidative cleavage. Oxidation because you oxidize it. What else did you do? You broke the pi bond. You could say you might even have cleaved it. No one's impressed. Okay, that's the term. Oxidative cleavage. You're oxidizing, increase the bonds to oxygen, and at the same time, completely break the alkene. Okay? And that's where we're going to add another step in here. Are we breaking the alkene? No, what are we breaking? I like the head shake, Tyler. What kind of pi bond are we breaking? I'll accept carbon-carbon. We can do better than that.
Non-polar.
Non-polar pi bonds. Okay? Alkynes are non-polar pi bonds. So if I throw these oxidative cleavage reagents at alkynes, are they going to do the same thing? Yeah. Okay? These reagents react with non-polar pi bonds to do oxidative cleavage. Okay? Take whatever that non-polar pi bond is, cut it in half, replace it with oxygens. Okay? Is it really that simple? Shockingly, yes. Okay? So, if we go through and take a look at the starting structure, this is what Carty's attempting to show here. Okay? We cut it in half, and what do? We replaced it with oxygens. I would argue there's a slightly better way to do this. Okay? Because he turned things. So we're going to draw the same thing. Okay? So there's my carbon. Except I'm going to make my pi bond really, 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 really long. Yeah, it was kind of loud. I heard it too. Really, really, really long pi bond. And now what am I going to do? Cleave it. Okay, by cleaving it. It's now cut. So I've done the cleavage part. What else do I need to do? I need to do oxidation. So what am I going to replace? I'm going to put oxygen in there. So there it is. If we erase my crummy drawing, what does Carty show? The exact same thing, just turned more upright. It's the exact same result. What happens with the alkyne? The exact same thing, right? Sort of. Okay, because Carty did a crap job of drawing this one, assuming I stole it from Carty. It looks kind of like Carty's work. Triple bond. 1, 2, 3, triple bond. There's our carbon. There's that bond. Cleavage. I keep doing that. Cleavage. What's that face? It's a good face. Okay, you're saying it makes sense. That's not what the picture showed earlier. That's because Carty drew a crap picture, number one. Okay, number two, there's something else going on here. Anybody looking at it being like, yeah, that's totally normal. I would totally expect oxygen to have a triple bond. No, why not?
Because oxygen doesn't.
Oxygen would be charged. So when we're talking about oxidative cleavage, we need to cleave it. Yes, cleaved. We need to replace those bonds with oxygen. Do they have to be the same oxygen? No. Oxygen's happy with 2 bonds, so what I'm going to do is fudging. Stupid eraser. I'm going to add another oxygen. What happens on the other side? Same deal. Oxidative cleavage. I've cleaved it. I've now made it happy. Do I like those single bonded oxygens out there?
Nah.
No. What might I do to help stabilize those?
Stick on a hydrogen.
Stick on a hydrogen. We've now done it. Cleave. Oxygens. That looks a little weird. Let's just throw some more oxygens in. Okay? While this seems incredibly simple and against all of our instincts that we've done this entire semester, this is exactly what I want you to do. Okay? So when you've been asking for shortcuts, ta-da, there they are. Eventually it had to happen, right? And you're shaking your head at me like, stop giving me shortcuts, go back to the other stuff. Okay? We can go back to the other stuff, actually, because we have that on the next slides. Okay? So what happens? Under hot, concentrated conditions, right? What occurs? Okay, well, step 1, the permanganate reacts. Okay, we get our manganate ester, right? There's our carbonyl manganate with our oxygen ester. So we have a manganate ester. What happens then? Oh, it just does that. What? How did that happen?
The 2 bonds to the manganate went to the oxygen instead.
Okay. We're under hot conditions. Okay. What might happen? What thing? Okay, and Lee and me know how to answer this question because they asked me about it. Heat does what to our reactions?
Makes them go
Speeds it up. It makes them go faster. And in particular, for those of you in lab that might have a lab quiz today, what did heat specifically do in our elimination reaction? What does heat do in our elimination reactions?
It makes them able to
Heat is used in particular to
break bonds.
what bonds are you breaking when you're adding that heat? The sigma bond, and in particular in the elimination reaction, the carbon-hydrogen bond. Why do we need heat to break the carbon-hydrogen bond?
Because it's a relatively strong.
It's a strong bond. It's a non-polar bond. That's a hard bond to go through and break. Okay, so we would need a strong base. But in the case of the E1, there's no strong base. So something needs to break it. You add a bunch of heat to help break that bond. Guess what heat's being used to do here?
Carbon-carbon bond.
To break the carbon-carbon bond. Those electrons come out to form the pi bond. The electrons shuttle to the manganese. The manganese now has too many electrons. So what happens?
Pushes it under the oxygen.
It pushes these electrons out. What's the end result? Ta-da! There it is. We've done our oxidative cleavage. Okay, this is an intramolecular elimination reaction. That's pretty freaking cool. The heat is what's allowing that bond to break. If we don't have the heat, that bond is not an easy one to break, and it doesn't break. Okay? So we have to have that heat to help allow for that to happen. Okay? Interestingly enough, it doesn't stop there. Okay? Because if we went back and looked at our permanganate, way back, Rocky and Bullwinkle, right? No? Okay. Carbonyl, carbonyl. What else is on here?
Oxygen.
Where the hell does that come from?
That's
Right.
it. So, well, wait a minute.
That was an alkene, not an alkyne. We said alkynes could form that OH. Okay. This is where the permanganate has some interesting chemistry, and that hot conditions helps. Okay? We are going to have, and it depends on the conditions you do it. This is why I said you got to watch out for the base condition. You can either run it basic or acidic. It doesn't really matter. But if we run under acidic conditions, this can come in and attack. Okay? The result is we form this structure. Okay? That carbon now has 2 oxygens connected to it. Is it happy with that? No, it's pretty reactive. Okay? And what we have here is a geminal diol, I believe. Okay? Don't stress about the word. Okay? Ultimately, diol. Really, the other name for this structure is a hydrate. Okay? Very similar to an acetal. Okay? That chemistry, if we look at the far right, is second semester chemistry. Once we've formed this hydrate, we have a diol. The diol is fancy because what can happen? It can react with the permanganate. You're like, no. What did we form here? That's 2 oxygens connected to the permanganate, right? We might call those 2 oxygens alcohols. Permanganate is reacting with the alcohols. As long as the alcohols are close enough to each other, it can react. Okay? Through a nifty little reaction that we don't need to stress about. Okay? Unless you want to. Which means the permanganate now connects. Now what happens? Water in solution removes the hydrogen. Where do the electrons go? To form a pi bond. But we've now exceeded an octet on the oxygen, haven't we? So what has to happen? The electrons would have to go to the manganese. That looks kind of familiar, but now the manganese has exceeded its octet, so what happens? The electrons shuttle back to the oxygen. The end result? Almost end result. You would have the carboxylate. You have that extra oxygen on there. Do we want a negative oxygen? No. This is where our acidic conditions come in. We add the final hydrogen. Okay. Shortcut or this?
Shortcut it is.
Just checking.
Shortcut it is, yeah.
Okay. So when we go through and deal with this, okay, how do we know we should be doing oxidative cleavage? Not because there's permanganate. We could try and tip off on the acid. Actually, there's a step 2. It says acid, so that's a pretty big hint. Okay, but I'm going to be extra obnoxious and be like, we're not going to show that. Concentrated. That word concentrated is a giant tip that what you need to be doing is the oxidative cleavage. Okay, so we will oxidatively cleave that. There's our big stretched out pi bond. What do? Cleave oxygens. Was permanganate like just a mild oxidizing agent, or was it gung-ho?
Gung-ho.
It was gung-ho. So what I would need to do is look at those carbons where the chemistry happened and see, are there hydrogens there? Yes. Which means what happens? Okay. The oxygen comes in and adds again, and we get that goofy hydrate structure that I was talking about. They were like, oh my God, I don't even want to have to worry about that ever again. Okay, but the end result did what? Turned that position into a carboxylic acid. So 1, 2, 3, 4, 5. What happens to the other carbonyl? Does it also have a hydrogen at that position?
Yes.
So what happens to it? Same thing, oxidize it. The end result? We get the diacid. Most common place for mistakes. So here we go. Here's answer choices for that reaction. Oh, well, here, you got the picture? I'm going to erase stuff. So if you want a picture, you should. Okay, I'm erasing. You get answers like this. Which of these is the right answer? A, B, C. That's exactly the problem, is everybody freaks out and can't track what happened. Okay, this was oxidative cleavage. Do we do anything to the carbons?
No.
No, all we do is oxidize the carbons. We just got to put oxygens on them, right? Okay, so we can go back through and look. How many carbons did I start with? 5. How many carbons should I end with?
5.
Which of my answers has 5 carbons?
A.
A. Make sense? Okay. It is incredibly common for students to lose carbons, particularly because you're following this little cheat. We just stretched it, drew it in. Remember, they're going to redraw the structures into that straight line format. Make sure you don't lose carbons through that process. Make sense? Okay. That one, we'll hook a little curve here. We stretch our pi bond. We erase out of the middle, oxygen, oxygen, okay? And then what?
Then it's concentrated, so...
It's concentrated, so we got to oxidize it. We get that as an answer.
That's a methyl bond.
Oh. So I just need to do this then.
Yeah, let's count that. 2, 4, 6, 8.
Still no.
That's
I've exceeded the octet on that carbon. Can I oxidize that position further?
No.
No. That blue carbon or blue dot carbon stops there. I can't continue to oxidize. It will stay as the ketone. The ketone is non-oxidizable because it doesn't have that extra hydrogen. Because to do an oxidation, what must you do? Add oxygen by removing hydrogen. Remember those 2 definitions we started with? That's how they're working. Okay? So to oxidize, you have to increase the bonds to electronegative atoms, but you also have to suffer the loss of hydrogens. Yes?
Can you oxidize the methyl?
All positions can get oxidized, and so this is the next thing. Every single one of these carbons can possibly get oxidized. What could they get oxidized to? Dude, I can't answer that question without knowing more. Yeah, you can. Because you've done it. Has anybody gone camping before? Yeah? Has anybody made a fire before? You've all oxidized. Oxidation reactions, have you exhaled?
Carbon dioxide, yeah. But I mean, like...
It's carbon dioxide. All oxidation reactions end at carbon dioxide. We can't oxidize them further. That structure is so insanely stable that becomes the problem with greenhouse gases and all sorts of other things, because we now can't reverse that process easily. Okay? So why not ask about continuing to oxidize? Well, we can continue to oxidize. The problem with that continuing to oxidize is destroying and ultimately uncontrollable. If we can't control it, we don't do it as organic chemists. Okay? We need our reactions to do what we want them to do and nothing else. If we don't have a control over that reaction, we tend to not do it. Okay? The same thing happens with our oxidation reactions. We can oxidize all organic compounds. It's called lighting a match and throwing it on our stuff. Okay? That works phenomenally well as an oxidation mechanism, but I can't stop it. Okay? So that's why we don't talk about oxidizing those other positions. Okay? There are other reagents that can do some of those oxidations. We'll worry about those another day. How many products do we get for the first one? Rhymes with?
2.
2. There we go. There's only 2 products in that first one. Okay? We only have one nonpolar pi bond that we can cleave. We can't cleave the pi bonds in the ring. Why not?
Because they're part of the band ring, the electron ring.
These are constantly in resonance. Those electrons aren't in a stable enough position for me to ever react, which means when I go through and do this reaction, I can stretch my pi bond. Sorry. That didn't get much better. Stretch the pi bond, benzene ring, close enough. Oxygen, oxygen. Do I have hydrogens? Yes, and? Yes.
Does that really matter anymore since it gets pretty much kicked out?
It depends. So we'll get the carboxylic acid, and what do we get for the other one? You might say, well, we form this structure. What is that structure?
Weird, and I've never seen it before.
Lies.
Oh, that's why I've seen it before. Yeah.
You get two products. You get that carboxylic acid and you get CO2. This is a common test question because what can they do? Which of the following are products of this reaction? They can show three crazy weird oxidation things that happen to not involve that structure. And then they write CO2. Like, well, there's no way it can be CO2. That's way too simple. Ta-da! Okay. So if you have a terminal alkene, why is this reaction used? This reaction is used because I have this big, large piece, but it has too many carbons. What do I need to do? I need to cut some carbons off. How could I do that? Put a terminal alkene, and what can I do to that terminal alkene? Permanganate, cut that last carbon off with CO2. I now have a smaller molecule. Like, why would you ever cut things apart? Has anybody had a haircut before? Okay. So we have the ability to not just add pieces on, but also take pieces off. Okay, make sense? How many products with the next one? Okay, because this is typically how it gets answered or asked. They would go 1, 2, 3, 4. I heard a suggestion for 2. I heard a suggestion for 4. Winner, winner, chicken dinner. 1, 2. So typically what happens is we go through and break that apart, and you go, oh, well, each of those breaks into 2 pieces. Right? So you go, oh, 1, 2, 3, 4, 5, 6. One of the answers is typically 6. Okay? Okay, so we go, oh, 6, but somebody said 4, so I didn't go with that one. Right? You have to realize that, yes, that cleaves, but that other piece is still there, right? I didn't get rid of that.
Answer to 3.
Right? So please be careful with these. The oxidative cleavage can be a little bit tricky to deal with. Okay? You'll also realize that we get CO2 coming out at the end. There's that one extra carbon out there. Okay? That very typically also gets ignored. Okay? You should be able to go through and draw those products. I'm not going to draw them, kind of for the sake of time, because in 7 minutes I want to cover like 7 slides. Okay? So, we have another oxidizing agent, ozone. Ozone does some really kind of cool, nifty stuff. Okay? It does that same kind of cyclic structure, and it forms what's known as a malozanide. Okay, why? I don't know, because it's fun to say. That structure is insanely unstable. Why is that insanely unstable?
Ring strain and just that much oxygen.
We get ring strain, oxygen-oxygen bonds. There's 2 oxygen-oxygen bonds in that structure. Okay? That is an exceptionally unstable structure, and it goes through some really crazy, weird, and bizarre, for lack of a better word, crap. Okay? Kind of nifty and crazy. I think it's kind of cool. There's no way in hell I would ever able to predict this. How was someone able to predict it? They did it repeatedly and tested for each of those intermediates along the way to see if they could find it. This is not someone sitting down and just cranking out some, structures. It doesn't happen that way. Okay? Where this ultimately ends up is what is known as the ozonide. Okay? The ozonide you might get tested on because that structure is somewhat stable. Okay? It is somewhat stable enough that we can now follow this reaction of ozone, okay, which is a step 1 with a step 2. Thank you, Cardi, for missing that. I sure hope he doesn't watch these videos.
1, 2, and 3. So that's
Oh, yeah, he's doing it, labeling it differently. So this is reagent 1. So I understand. Okay, sorry, Cardi, you're right. Now I'll modify. Okay, step 1 or reactant 1, ozone. Step 2, we can follow it up with another reagent. Okay, what is this reagent doing? Well, let's take a look. The end result is what happened. What's our overall reaction? We started with the alkene and ended here. What did I do? I cleaved and oxidized. It's an oxidative cleavage reagent. Ozone does that. Neato. Anybody else notice something else interesting about this? There's a hydrogen there. Not only did ozone do oxidative cleavage, but what did it not do? Continue to oxidize. It actually stopped. Ozone has control. What does that mean for the usefulness of ozone?
that we like to use ozone rather than.
Ozone is now going to be a more common reagent for synthesis because I can control how much it oxidizes. Right? Anybody knows something else interesting about this? Let's take a look at the ozonide. How many oxygens are in that? 3. How many oxygens are in our alkene or our oxidative cleavage product? 2. What the hell? Where'd the other oxygen go? That's what that last reagent did. That last reagent scavenged one of those oxygens, preventing it from reacting. Okay? That compound is very commonly named. Okay? We have a sulfur compound, so those get named as sulfides is our primary functional group. What are the substituents on that sulfide? Okay. We have methyls. It's a dimethyl sulfide, also known as DMS. Do we still have DMS in the end?
No.
Do I still have 2 methyls? Yes. Do I still have an S? Yes. So I still have DMS, but what else have I added? An oxygen. This compound now becomes, thank you for ruining the punchline, DMSO, dimethyl sulfoxide. Okay? So they sometimes will make reference to that second step. Okay? What else is produced? DMSO. Okay? You need some kind of oxygen scavenger if you want it to stop oxidizing. What if you don't have an oxygen scavenger? Then it will continue to oxidize, and it will oxidize that position out to a carboxylic acid. Kind of, sort of? Okay. So that's where our ozone comes in handy. Okay. Under these conditions, you'll notice, what did I add? Step 2 was hydrogen per oxide. What did I add? I added more oxygen. Is that going to stop oxidizing?
No.
No. You add more oxygen, continue to oxidize. Okay? So when you go through and look at it, your reductive oxidative cleavage is DMS. Say that again. The reductive oxidative cleavage.
DMS.
Reductive oxidative. Is a reaction an oxidation or a reduction reaction? It's oxidation. It is only oxidation. Why do we call it reductive?
Because we're reducing the oxygen, but otherwise continue.
That'd be cool.
we could have continued to oxidize, but we didn't. So when you're hearing the reductive oxidation, it's still an oxidation reaction. We aren't doing a reduction. We just stopped oxidizing. That's what they're trying to reference. Okay? So the reductive conditions, you need DMS. Oxidative conditions, pretty much anything with oxygen. Okay? If you see oxygen in that step 2, oxidize it. If you don't see oxygen, you should probably leave it in that reductive state. Okay? Don't take it all the way to the carboxylic acid. Okay? So quick modification. Do I still end with a carboxylic acid?
No,
Why not?
because you've got a carbon and not an oxygen. You need a stronger oxidizer, wouldn't you?
Nope. Why do I not end with a carboxylic acid? We have to look at the position that was reactive. That's now the blue carbon and the blue carbon. Do those blue carbons have hydrogens to remove? No. We don't go to the carboxylic acid because I can't oxidize anymore. There's no more hydrogens to remove from that position. Okay? So it stalls at that point. So when we're looking at this reaction, oxidative cleavage, cleave it, put oxygens on there, evaluate, are there more, could you oxidize more? If you can oxidize more, then you got to evaluate your reagents a little bit more carefully. Should we be using ozone or permanganate for this one? Doesn't matter. Both of them will stop at this oxidative product.
So you have to lose, you have to be able to lose.
You have to be able to lose a hydrogen at that position to oxidize it further, yes. Okay, and with that, we'll have to stop. I think we've finished. I didn't do any of the reduction stuff. Oh well. Okay.